Hello, let's do nuclear fission and then nuclear waste. Now what's nuclear fission? Well, that's pretty much the opposite to fission. Fission was a big nucleus breaking apart into smaller ones. Fusion is little nucleuses banging together, combining to make bigger nucleuses. It's what's happening in the sun right now to make the heavier elements. And so typically when we talk about fusion, we're pretty much talking about the synthesis of helium-4, and we're getting that from the two isotopes of hydrogen, tritium and deuterium, and we force those guys together and we get the helium nucleus, and we get a neutron given off, and energy is also given off because there's a conversion of mass again, and that mass goes into pure energy. E equals mc squared is the equation that governs that. So two diagrams just showing pretty much the same thing. And so this is where the energy would be released. Now how do you do it? No one's done it, or there's no active nuclear reactor around that's using fusion. All the nuclear reactors use fission. However, they're designing one, and it's being built in Europe, and it's very different design from a nuclear reactor fission one, in that basically to get this to occur you've got to get the isotopes up to temperatures of around 100 million degrees, and so you end up with this super hot plasma, basically as hot as the surface of the sun. And how do you contain that plasma? Well, it's not allowed to touch any sides of the chamber because it would just melt its way through. So they use magnetic fields to actually control its shape. And then how do you put things into the plasma and take things out if you can't touch it? Very complicated engineering. They made a small scale fusion reactor, the Tomamark I think it was called, and it sustained fusion for a couple of seconds, and so that was a proof of concept idea. And so they then decided, a consortium of countries decided to pitch in some money and build a full-size model of a working fusion reactor. And this is the this is the Tomahawk one, which was the proof of concept. And so this would be the chamber that would have a plasma floating around in it. Now people have worked with plasmas before. Your good old garden variety fluorescent tube is a plasma, but in this case much different, much higher tech, and basically it's got to be held up by magnetic fields. Then you've got to have heat extractors to extract the heat, because you've got to run turbines to generate the electricity, and then you've got to put in new isotopes to resupply the fuel and take out old ones. But this is the scale of the test one, and there's a video on it, on the process, on your OneNote. And then the actual fusion reactor they're making is called ITER, and that's the previous one. And this is the scale. There's a human being for scale, so significantly bigger. And this is a model of a working nuclear reactor where they hope that the energy they get out will be greater than the energy they put in, and therefore it's a generator, and they will be able to sustain fusion for significant periods of time, well, continuously basically. And so it's being built in Europe at a cost of a few $billions, and there's a couple of interesting videos on it that probably explain it way better than I can. Now, they're not the only ones trying to generate fusion on Earth, and there's a thing called the National Ignition Facility in America, which is using lasers to try and initiate fusion, and they're still doing a proof of concept, and so a couple of videos will show you what they're trying to do and how they're doing it. Basically, they're firing very high powered lasers into a very small sphere, and they're going to the lasers are going to compress that sphere to a point where fusion occurs and energy is released. But a very, very complicated way of doing it with lasers, but a lot of the cutting edge technology that relating to lasers is actually coming out of this facility here, because they've had to design new stuff to do what they want it to do. Now, so that's enough of all that, and we're just going to move on to nuclear waste. But before we do that, this is your typical radioactive warning sign. People recognize that, but some people said, well, we have a problem, because although we recognize that, if you dropped a whole lot of these things into some community that had never encountered radioactivity and had never learnt about radioactivity, if you showed this sign to them, they wouldn't understand what it meant. And therefore, that presents a problem, because when you're dealing with nuclear waste, particularly the waste from fission nuclear reactors, that waste is radioactive for tens, if not hundreds of thousands of years. And if we think back just a couple of thousand years, we aren't all that far gone in terms of civilization. If you go back 3,000 years, where were we? Pretty much very simple civilization to what we are now. So in 100,000 years, who knows what it's going to be like. And so we need some new symbols, and they started off just thinking, well, we need to redesign this symbol to something that people understand, and they came up with this one, which is a combination of symbols. Basically get rid of the nice warm fuzzy colour of yellow, which, although it draws your attention, doesn't necessarily mean alarm, whereas red is a more colour of alarm. They've still got this radioactivity symbol, but they've got these invisible beams that clearly cause something nasty, and this is supposed to mean run away. And so, yeah, haven't seen many of these being used yet. I think it's still a concept being developed. But what do you do with high-level nuclear waste? Well, at the moment, all the countries that have nuclear reactors or use nuclear medicine have problems with their waste. Basically, they're either storing it above ground in drums and tanks, or they're burying it in drums or tanks. But if you asked any of them whether they were a permanent solution, they'd all say, well, no, this is only a temporary way of storing it until we come up with something permanent. But only a couple of countries are actually building permanent nuclear waste facilities. One of them is Sweden, and I think Finland. They're building some. I think France is building one. America was building one, but it stopped. And this was the actual idea, the concept of the American one. And this is for storing the most radioactive, most dangerous materials that come out of nuclear reactors. Now, I did forget to mention when I was talking about fusion, was the other advantage of a fusion reactor is that it doesn't produce materials that are radioactive for tens of thousands of years. Some of the paneling might become radioactive because it gets bombarded with neutrons, but it will only be a low-level radiation for tens of years, and therefore it's the problem of nuclear waste from fusion reactors is pretty much non-existent. Whereas when you shut down a fission reactor, the core and many of the materials that were being used are going to be highly radioactive for tens of thousands of years, because they're different isotopes you're talking about and different decay rates. So this is a planned one in America, and the plan is to have a surface facility and then basically dig down into salt beds that are basically rock made of salt, and to deposit all the waste inside here and then fill it up as they go and hope that it doesn't interact with groundwater or faults don't occur or things like that. And so it's very hard to find something that you can be 100% certain is going to be geologically safe for 100,000 years. 100,000 years is long enough for geology to take place, earthquakes to occur, and lots of things to happen. And so it's very difficult. Now, the other problem was also in 50,000 years, this surface structure will have gone, would have been obliterated just by time. And therefore, how do you warn people not to dig in this area? Because they might actually be looking for minerals or looking for something, and stop people from digging in this area and exposing themselves to extreme radiation. And so what these people were proposing as part of their plan was to sort of do a variation on the pyramids. Basically have monoliths up there, and then have a structure of monoliths, so that people would go, well, this is weird, we need to study this a bit more, we need to work out what's going on in this site before we do anything. And because how do you convey? There's no guarantee that we'll actually be using the same language, the same symbols as we are now. And so communication will have evolved to such a extent that they may not be able to read English or any of the other languages that we have right now. So they have these monoliths, and then they have a central chamber, and in the central chamber they have a hot cell and a burial, storage, and an information room. And the hot cell is a little mini example of what you'll find underground, so they're trying to show that this will be radioactive. And the monoliths will try and have warning signals on them and then be buried as well, so that they can't fall over, and all sorts of long-term planning. Then you sort of have a crypt, and inside the crypt you have more messages trying to convey, and then it's sealed with a great big plug, so that there's only one way in, and once you go in, so you got sort of, they're trying to make people treat it with respect and explore it, so they can work out what's actually underneath the surface. Pretty amazing way of thinking about it. A map showing other deposit sites around the world, trying to explain not to dig there and elsewhere. Okay, and their warning signals and stuff. Now, where is this? New Mexico, they're planning to build it, and the scale is something like 4 miles across. So they have this big circle of monoliths, sort of like a Stonehenge meets the pyramids type scenario. Pretty interesting, but I don't think it's actually got go-ahead. They said no, too dangerous. Well, the local community didn't want it, and so they're actually, America still hasn't come across a site where they can store their nuclear waste, and they're one of the major holders of high-level nuclear waste. Right, that brings us to the end pretty much of radioactivity. If you've got any questions, feel free to ask me. Make sure you're in tune with everything we've tried to learn, and make sure you go to the OneNote and watch all the bits and pieces that you have to, and then we're going to do a whole lot of questions to put it into practice. So that's it. See you later.